In our last section of chapter 4, we are going to discuss the binomial and geometric probability distributions. So we're going to start with the binomial distribution. So there are a lot of experiments and situations that result in something that is called a dichotomous response, which means that the responses, there's only two possible choices. So true, false, yes, no, defective, non-defective, male, female. There's a lot of options. So a very simple example of this is tossing a coin, where there's only two possible outcomes, heads or tails. So there's many other types of experiments similar to a coin toss where you're observing the success or failure of a certain outcome. And such experiments give us a probability distribution that is more specifically called a binomial distribution. So in order for something to be a binomial distribution, there are 4 conditions it has to meet. So the first one is that each observation falls into one of 2 categories. We call them success or failure. Now, success doesn't necessarily mean positive. So if you're looking for the number of people who get colds after being doused with water on a winter day, success might be defined as getting a cold. So success is just the affirmative or the positive of whatever your situation is. It's not necessarily going to be good. The second is that there has to be a fixed number of n observations. The third is that the n observations are independent. So knowing the result of one observation tells you nothing about the other observations. And lastly, the probability of success p is the same for each observation. Now 3 and 4 are really going to go together because if the observations are independent, typically the probability of success does not remain the same. So 3 and 4 are going to go together. And the 2 that we're most often going to probably run into not a binomial experiment is going to be with 1 or 2, which is why we go in that order. So for the definition of a binomial distribution, it is the distribution of the count x successes in the binomial experiment with parameters n and p. And the possible values of x are integers from 0 to n. So here, n, just to kind of remember, is your number of trials. And p is your probability of success. So we're going to go through and we're going to determine whether or not our example is a binomial distribution or not. And if it's not, we're going to specifically state why it isn't. So for our first example, we are looking at tossing 20 coins and counting the number of heads. So the first kind of requirement is that each observation falls into one of 2 categories. And here we have 2 outcomes, heads and tails. So we have met the first condition. For our second condition, we have to have a fixed number of observations. Well, we're flipping a coin 20 times, so we do have fixed observations. The third is that each outcome is independent. And we've already discussed the fact that coins are always going to be independent for us. And then for your probability of success remains the same. So p is going to be 0.5 for every flip here. So all 4 conditions are met, which means we do have a binomial distribution. In our second example, we have that you're picking 5 cards from a standard deck and counting the number of hearts. We are going to replace the card each time and reshuffle. So for our first condition here, do we have 2 outcomes? And technically the answer is yes, because we are looking to see whether or not we have a heart or not a heart. So even though there are 4 suits, we're only counting the number of hearts. So if it's not a heart, we're saying, nope. For our second condition, we are drawing 5 cards, so we have a fixed number of outcomes. For our third, now here's where we have to get kind of specific. Because it states that we are replacing the card each time and reshuffling, we can say the cards are independent. If we weren't replacing the card, we would run into problems, and also if we weren't reshuffling. So then the fourth one, the probability of success is going to remain the same, 0.25, because there are 4 suits. So there's a 25% chance on each draw you get a heart. So this is a binomial distribution. All right. So in our third example here, we're still picking 5 cards from a standard deck and counting the number of hearts, but now we're not reshuffling the deck each time. So in this case, our first 2 conditions are still met because they're the exact same as our previous example. The issue becomes in steps 3 and 4. So now my cards are no longer independent and my probability of success is not 0.25 because you are not reshuffling. So now it is not a binomial distribution anymore. Okay. Our last example here, you're choosing a card from a standard deck until you get a heart. So very important wording here is the until you get a heart. So this changes our second condition. So my first condition is still met because we still are looking at whether or not you have a heart or not. But the second condition is no longer met because we don't have a fixed number of trials here. Because we're going until we get a heart, that could happen on the first draw. Maybe it happens on the 30th draw. Like, who knows at what point it's going to happen. So this is no longer binomial. And I don't even need to check conditions 3 and 4 because condition 2 is not met. So you don't have to check all 4 if the first or second condition isn't met. You only need to keep checking conditions if they are met. So let's talk about how we calculate binomial probabilities. And we're going to start by doing an example with this. So Calvin is about to take a 5-question true-false quiz for which he is not prepared. So he will be guessing on all 5 questions. So we want to figure out the probability he gets all of the answers correct, all of the answers wrong, exactly 3 answers correct, which would be passing in this case. So he passes because 3 out of 5 is 60%, and that he will pass the quiz, which is it's the exact same thing as number 3. So 3 and 4 are the exact same question. So we're going to start by how you would do this by hand if we didn't know that this was a binomial distribution. So we're going to let C be a correct answer and W be a wrong answer. And we are going to list all of the possible combinations of correct and incorrect responses on this quiz and make our probability distribution of them. So X is going to be the number of correct responses. So X, and then we'll have our probability of X down here. And then we'll have our outcomes. Okay. So when it comes to X, he can get 0, 1, 2, 3, 4, or 5 of the questions correct. So if he gets if he gets 0 of them correct, that means he got 5 wrong. So that is 5 W's, which there is only one way for that to happen. So the outcome is 1. We'll come back to the probability at the end because we do need to know how many total outcomes we're going to have. If he gets 1 question correct, so it could be that he gets the first question correct and the rest wrong. It could happen that he gets the second correct it could be that he gets the third, he could get the fourth, or he could get the fifth. So that correct answer, there are 5 different ways he could get that one answer correct. For 2 of them, so he could get the first 2, he could get the first and the third, he could get the first and the fourth, or he could get the first and the fifth. And I'm not going to keep going these because it keeps going. Just know there are 10 outcomes for getting 2 correct. All of the different combinations of if it's the first or if it's the second and the third, the second and the fourth, the second and the fifth. You just keep moving your way down the possibilities. X equals 3 is going to be the same as 2, but the C and W are switched. So still 10 outcomes for that. For 4 of them correct, that one's a little bit easier because it could be that he gets the first 4 correct. It could be that he gets the first wrong and then the last 4 correct. And then we just basically move that one wrong answer down in the line. So there are 5 ways. And then for him to get all 5 of them correct, there's only one way for that to happen. He gets all 5 of them correct. So if we add up our total amount of outcomes here, we're going to get 32 total outcomes. So now I just put my numbers over 32. So there's a 1 in 32 chance he gets none of them correct. 5 out of 32 chance he gets 1. 10 out of 32 that he gets 2. 10 out of 32 that he gets 3. 5 out of 32 he gets 4, and 1 out of 32 that he gets all 5 of them correct. So it's very, very similar to the example we did when we were flipping a coin 3 times and looking at the heads and tails, but now instead of having just the 0, 1, 2, or 3 when we're counting our number of heads, we went all the way up to 5. So now let's go back to our original questions that we had. So the probability he gets all of the answers correct. So that's the probability that X equals 5, which in this case is 1 out of 32. The probability he gets all of them wrong, so the probability that X equals 0, also 1 out of 32. And then exactly 3 correct, so that's going to be the probability that X equals 3, which is 10 out of 32. So that's the bare minimum to pass. Now, the actual question, he will pass the quiz. So that's the probability X is greater than or equal to 3. Because he can pass the quiz with 3 of them correct, which is a 60%, 4 of them correct, which is an 80%, or 5 of them correct, which is 100%. So we do 10 out of 32 plus 5 out of 32 plus 1 out of 32, which gives us 16 out of 32, which is 1/2. Now, that was all very, very time consuming because you have to go through all of the possible outcomes. And if as n gets larger, so 5 questions versus what if it was 10 questions or even 30 questions, like it can get very time consuming to calculate it by hand, which is why we're also going to talk about the formula. So we're going to talk about how you do the formula by hand, but we're also going to talk about how you can do it on the calculator as well. Because even using the formula by hand can get a little bit time consuming, especially if you have to do a greater than or equal to or less than or equal to situation. So if X is a binomial distribution with n observations with your probability of P on each observation, and your possible values of X start at 0 and go all the way up to n, and R is one of those values, the probability that X equals K is given by the formula. So probability x equals k, and we'll get to what the variables mean here in a second, is going to equal n choose k. So that gives you all of your possible combinations of getting questions correct and incorrect, times the probability to the kth power. So what's the probability of success? And then you want to get those numbers correct, times 1 minus p to the n minus k. So 1 minus p would be, all right, what's the probability I don't get it right? And then n minus k represents how many problems you're getting wrong. So we use the NCK, which is from our previous section with combinations and permutations in 2.5. We know is going to be the formula n factorial over k factorial times n minus k factorial. So that's your combination. So n is our number of trials. K is our number of successes. And P is the probability of success. Okay. Just to kind of remind you here how to get to the combination formula on your calculator, the NCK, you go to Math, and then either PRB or PROB on your calculator, and then number 3. So it's the NCR. All right. Now I'm going to kind of explain each piece of the formula. So I'm just going to rewrite it here. Probability x equals k. So I'm going to go ahead and explain each part. So the probability x equals k is your probability of k successes. So you're saying, all right, what's the probability I get 1 correct, 2 correct, so on and so forth. Then we have NCR, which is your combination of k successes in n trials. Then we have p to the k, which is your probability of success raised to your number of successes. And then the last one, 1 minus p to the n minus k, which is your probability of failure. So that's what 1 minus p is, your probability of failure, raised to the number of failures. Sometimes we are going to see 1 minus p represented by q. Q can also represent your number of failures. So instead of writing 1 minus p, sometimes we also write q instead. So that's just in case you see it somewhere else, q equals 1 minus p. So now instead of having to create that entire table, now we're going to go ahead and calculate the probability that Calvin gets exactly 3 correct and the probability he passes using our formula. So the probability that x equals 3, we're going to do 5 choose 3, because there were 5 questions, we want 3 of them correct, times the probability of success is 1/2 because it's a true-false test, so 1/2 to the 3rd, times probability of failure, also 1/2 squared. So if we go to our calculator, we go to the NCR, I do 5 choose 3 times 1/2 cubed times 1/2 squared. It might give you a decimal, 0.3125, which is fine, but if you convert it back to a fraction, you get 5/16, which I didn't simplify it on the previous page, but 5/16 is the same thing as 10/32. Here's where the binomial distribution can get very time consuming. It's if you want to do an equal, greater than or less than situation. So the probability that Calvin will pass, so the probability that x is greater than or equal to 3. We have to do the probability that x equals 3 plus the probability x equals 4 plus the probability that x equals 5. So I would have to do the formula 3 times and then add them all together. So we already found the probability that x equals 3. That's the 0.3125. The probability that he gets 4 correct, 5 choose 4 times 1/2 to the 4th times 1/2 to the 1st, and then plus 5 choose 5 times 1/2 to the 5th times 1/2 to the 0. So that's where it can get time consuming, because if I had done greater than or equal to 2, I would have had to do even more. You still end up with 0.5, which is 1/2, just like we did on the previous example. So when you have a greater than or equal to situation, or even a less than or equal to situation, using a formula on your calculator is actually going to result in less work. If I'm doing a single outcome like x equals 3, that one's not too bad. I just have to do the formula once. But when an inequality is thrown into the mix, it gets very, very time consuming. So having a shortcut on your calculator is going to be very beneficial. So on your calculator, we are going to look at calculating a binomial distribution on the calculator. So in order to get to the formula, you do second vars. And then we're actually going to be looking, if you keep scrolling down, we are going to go to the letters A and B. So A is going to say binom PDF, and B is going to say binom CDF. Okay? There is a difference between those two formulas. So binom PDF is our regular probability distribution. So it's used specifically when you want to find the probability that x equals k. And the only thing you need to know is n, p, and k. So let's go ahead and do that example, that probability that Calvin gets exactly 3 correct using the formula on our calculator. So we'll go to binom PDF. Okay. N is going to be 5. So our trials are 5. Our P is going to be 0.5. That's our probability of success. And our X value is going to be 3. So this is our trials, P, and X value. And then you might have to hit paste, or you might have to separate with commas depending on your calculator. Then you hit enter and you get 0.3125. Our second equation is the binom CDF, and that stands for cumulative distribution. And it's used when you're trying to calculate the probability of an interval of values. Now, very important thing here is that it is specifically when x is less than or equal to k. Unfortunately, it does not do greater than or equal to. It only does less than or equal to on the calculator. So when you have a greater than or equal to inequality that you're trying to find, you have to convert it to a 1 minus. So the probability that Calvin will pass is the probability that x is greater than or equal to 3. But since our calculator won't do x greater than or equal to 3, I have to change this to 1 minus the probability x is less than or equal to 2. So it's 1 minus the probability he fails. So 1 minus probability fails. So think of it in terms of that. So he fails if he gets 2 or fewer questions correct. So in the calculator, it's binom CDF. Our trials are 5. Our probability is 0.5. And then we're going to plug in 2 for K. Now you can do this one of two ways. You can find the binom CDF first and then do 1 minus, or you can set up the 1 minus to start with. It's really up to you. So it becomes 1 minus 0.5, which is 0.5. So you still get the 0.5. Okay. So a couple things here. Binomial random variables are discrete, which means the inequalities matter. And because the calculator only does less than or equal to, you have to make sure that every time you are looking at an inequality, the one that you use in the calculator is less than or equal to. So, for example, if I had the probability that x is less than 3, that is the same thing as the probability of x less than or equal to 2. So you have to convert a strictly less than to a less than or equal to situation. On the reverse side of things, if I had looked at the probability x is greater than 3, that becomes 1 minus the probability x is less than or equal to 3. So if it's a strictly greater than, you have to do 1 minus and it actually stays the same number and it becomes less than or equal to. So make sure you're paying attention to your greater than, less than, or equal tos when you do it in the calculator. All right, so let's just do a couple general examples. So we have a binomial distribution with a probability of success of 0.4, and we're doing 5 trials. And we're going to use our calculator to find the following probability. So the first one is the probability x is less than or equal to 1. So I can go ahead and just do binom CDF. My number of trials is 5. My probability of success is 0.4, and then 1. And we're going to get 0.33696. Most of the time, these are going to come out as decimals. And so you can leave them as decimals. If you wanted to convert it back to a fraction, you can, but I'm not going to require it. The probability x is less than 3. So that is the same thing that as the probability x is less than or equal to 2. So we're going to do binom CDF with my trials of 5, my probability of 0.4, and this time 2 as my number, my x value, which is going to give us 0.68256. For the probability x is greater than or equal to 4, I have to change that to a 1 minus situation. So that's 1 minus the probability x is less than or equal to 3. So if I go ahead and I do binom CDF with my 5, my 0.4, and my 3, I'm going to get 1 minus 0.91296, which is going to be 0.08704. Now the probability that x is greater than 4, considering there's only 5 trials here, you have 2 choices. The probability x is greater than 4 is the same thing as the probability x is 5, since 5 is the only other option that's greater than 4. Or you can think of it as 1 minus the probability x is less than or equal to 4, if you want to do the binom CDF. No matter which one you do, you're going to get the exact same answer. So if I do the binom PDF with 5.4 and 5, I get 0.01024. And if I do the 1 minus binom CDF with 5.4 and 4, it becomes 1 minus 0.98976, which is also 0.01024. So both of those correct ways to do this last example, specifically because there is only one number greater than 4 in this distribution. It would have worked the exact same way if I had said, what's the probability x is less than or equal to 1? The only thing less than or equal to 1 is 0. So I could have done less than 1. I could have done binom PDF with 0, or I could have done binom CDF with less than or equal to less than 1. It's the same thing. Okay. So the last thing we're going to discuss with the binomial distribution is the mean and standard deviation. And these are very, very easy formulas. They're a lot easier than the traditional mean formula and standard deviation formula, and even the formulas for the probability distribution we discussed in section 3. So for the mean of a binomial distribution, you just multiply n and p. So your number of trials and your probability of success. The standard deviation is the square root of n times p times q. So number of trials times the probability of success times your probability of failure. So here's where that q equals 1 minus p situation. So for Calvin's quiz, we want to find our expected value, which is our mean, and our standard deviation. So how many questions is he expected to get correct? And then how much does that typically vary by? So 5 times 1/2 is 2.5. And for our standard deviation, we do the square root of 5 times 1/2 times 1/2, which is 1.12. So for the mean, that tells us that if Calvin took many of these quizzes, we would expect him to get 2.5 of them correct. So, ooh, that's my highlighter. So if Calvin took many quizzes, we expect him to get 2.5 questions correct. For our standard deviation, that means that the typical variation in number of correct answers is 1.12 questions correct. So you interpret the exact same way we interpreted expected value and standard deviation when we were talking about just a general probability distribution in section 3. Let's look at one last example. So suppose that the probability that any random freshman girl will agree to go with Nick to the senior prom is 0.1. Suppose Nick asks 20 random freshman girls to the prom. What is the probability that exactly one will say yes, that at least one will say yes, and then on average, how many girls will agree to go with Nick to the prom? And then what's the standard deviation? So let's start with the first question. The probability that exactly 1 will say yes. So that's the probability that x equals 1. So if we do binom PDF on our calculator, so second bars, and then we go to binom PDF, our number of trials is 20, our p is 0.1, and our x value is 1. It's a very long decimal, so I'm just going to round it to 2 decimal places. If you wanted to go 4, it's 0.2702, but there's about a 27% chance that someone will say yes. The probability that at least 1 will say yes, so the probability x is greater than or equal to 1, that's 1 minus the probability that x equals 0. So in this case, I'm going to do binom PDF again, but this time my x value is going to be 0, and I'm going to do 1 minus that, and we're going to get 0.8784. So there's a very high chance that at least one of them will say yes to him. So on average, how many girls will agree to go with Nick? So our expected value, we're going to do 20 times 0.1, which is going to be 10. So, sorry, 2. So you only expect 2 girls that are going to say yes. And then our standard deviation is the square root of 20 times 0.1 times 0.9, which is going to be 1.34. So the second distribution we have to talk about is the geometric distribution. So the difference between a binomial and a geometric is based on the wording. So in a binomial distribution, x is the number of successes in a fixed number of trials. But in a geometric distribution, we use the variable y, and it's the number of trials until you get the first success. So we're specifically looking for the first success in a geometric random variable geometric distribution, and in a binomial, we're looking for a specific number of successes. So a couple general examples of this is you flip a coin until you get heads, you roll a die until you get a 6, or you throw darts at a dartboard until you get the bullseye. So until is going to show up a lot of times in a geometric distribution, because that usually indicates that you're doing something until the first success. So a geometric distribution does have some conditions just like a binomial. Some of them are the same. So the first one is that it does have to be binary. So just like with a binomial random variable, each trial has to have only 2 possible outcomes, success or failure. It does need to have independence. So the trials have to be independent of each other. So those 2 are the same. Here's the third one that is different. Instead of having an n, which is your specific number of trials, you have a number of trials until the first success. So instead of having an n, you have the number of trials to reach the first success. And the last one is your probability of success. So the probability of success does need to stay the same. So 3 of the 4 conditions are the same. Has to be binary, only 2 options. You have to make sure each trial is independent. The probability of success has to remain the same. So those 3 are the same, but instead of having a fixed number of trials, you now have a number of trials until the first success. So let's go ahead and look at an example. So we're going to look at a die example. So you roll a 6-sided die, and y is our number of trials until you roll a 6. So we're going to kind of do this this is similar to what we did the binomial by looking at an example without a formula. So we want to know the probability that you roll a 6 on the first trial. Well, that's pretty straightforward. There's a 1 in 6 chance that you roll a 6 on the first roll. Now, what's the probability that you roll another number on the first trial, but a 6 on the second? Well, so any other number has a probability of 5 out of 6 times the second roll being a 6, which is 1 out of 6. So that gives you 5 over 36. Now suppose that you did some other number on the first two, but a 6 on the third. So that's 5 out of 6 times 5 out of 6, then times 1 out of 6, which is going to be 25 over 216. So if I wanted to set this up as a probability distribution, where x is the number of y, because it's geometric, y is the number of rolls until you get a 6, and then your probability of y. So it happening on the first roll is 1/6. It happening on the second is 5 out of 36. It happening on the third is 25 over 216. And then we could keep going if we wanted. So here's another place where we kind of differ. Can y be 0? So with a binomial distribution, you always start at 0 and you go until n. But in a geometric, y can never be 0. Because if we're looking for success in a number of trials, you can't have your success happen on the 0th trial. That makes no sense. So you need at least one trial for there to be a success. The second thing is, when do we stop the table? So with a binomial distribution, you had a specific number of trials you were looking at, so you had a specific number of x's. With y's, because you could technically keep going, you don't stop the table. The table can technically go on forever, so there's no end to a table. So we don't create tables for a geometric distribution because it would go on forever. And then if we're kind of looking at my pattern, so my probability of success is 1 minus the probability of success to your number of failures times the probability of success. So I was looking for my first one, I had no failures, so it was just P. For my second one, I had 1 failure, so that's where I got the 5/6, then my success. Then 2 failures. So this formula is a lot simpler than the binomial formula. So if y is a geometric distribution with your probability of success P on each trial, and K represents the trial that you want to get your first success, the formula of probability the y equals K is 1 minus P to the K minus 1, because it always happens on one less trial, times your probability of success P. So for our first example, let's say we want to find the probability that it takes you 5 rolls until you get a 6. So that's the probability that y equals 5. So that means we had 4 trials of failure, so that's 5/6 to the 4th, and then our 1 trial of success times 1/6. So again, it may give you out a decimal, it could give you out a fraction. I don't care which one you give me. So as a decimal, it's 0.0804. But as a fraction, it's 625 over 7,776. So decimals are a little bit nicer in this case. Next, let's find the probability it takes you 10 rolls until you get a 6. So that's the probability that y equals 10. So that means I had 9 failures, so 5 6 to the 9th, before my success. So 5 6 to the 9th times 1/6 is 0.0323, which, because this is such a small number, it's not really going to give you a fraction. It'd be 5 to the 9th, which is 1953125 over 6 to the 10th, which is 604,66176. So very not fun fraction, which is why we typically go with decimals when we're doing a geometric distribution. So let's talk about an inequality with a geometric distribution. So what is the probability that your 6 happens within 3 rolls? So that's the probability that your success, y, is less than or equal to 3. So that means that it could happen on the first roll, the second roll, or the third roll. Which this one's easy enough to do. So we already know the probability it happens on the first roll, which is 1/6. We also know the probability it happens on the second roll. That was 5 over 36. And we also calculated the probability it happens on the third roll, which was 25 over 216. So I add those all together. And we get 0.4028, or 29 over 72. Let's talk about the probability that it takes at least 4 rolls to get a 6. Now, unlike a binomial distribution where I could say, oh, I'll just add these ones, because with a geometric it goes on forever, if I want to find the probability that y is greater than or equal to 4, I have to change it to a 1 minus situation, because I can't do greater than or equal to in a geometric distribution because it goes on forever. So I have to change it to 1 minus the probability is less than or equal to 3, which we already found. So 0.4028, which is 0.5972. If you do it in terms of fractions, 1 minus the 29 over 72, you get 43 over 72. So just like a geometric distribution, there is, a binomial distribution, there are geometric formulas on the calculator. So you go to second vars, and then the geometric distributions, you want to keep going, and they are F and G. So F is your geomet PDF, and G is your geomet CDF. Okay. And then the only things you need to know are your probability of success P and your number of trials K. So just like with the binomial, PDF is your exact and CDF is the less than or equal to. Last thing we're going to talk about is mean and standard deviation of a geometric random variable. So the mean, or the expected value, is 1 over P. So how many trials do we expect to run before we get our first success? And then our standard deviation is the square root of Q over P. So again, Q here is our 1 minus P. So that's the typical number of trials that deviate from the mean. So you do the square root of your failure over your probability of success. So for example, we have that to start her old lawnmower, Iris has to pull a cord and hope for some luck. On any particular pull, the mower has a 20% chance of starting. So using our calculator, we're going to find the probability that it takes her exactly 3 pulls to start the mower. So that's the probability that y equals 3. So we're going to do Geomet PDF. And then our p-value is 0.20 and our x value is 3, which is 0.128. You can also use the formula here. So 0.8 squared, because that's the probability her first 2 pulls fail, times 0.20. For B, we want to find the probability it takes her more than 10 pulls to start the mower. So that's the probability that y is greater than 10. So I have to convert this to a 1 minus situation. So I'm doing 1 minus the probability that y is less than or equal to 9. So we're going to do 1 minus Geomet CDF with 0.20 and 9. So we're going to get 1 minus 0.8658, which is 0.1342. And then how many pulls do you expect it will take Iris to make? So that's our expected value. So our expected value, or our mean, which is 1 over p, so 1 over 0.20. Which is 5. So we expect it takes her 5 pulls to start the mower. Let me know if you have any questions about the binomial or geometric distribution, whether it's telling the difference between the two, the formulas, or using your calculator.